Hi, I'll try to give a brief intro into physics-informed neural networks. First of all, an overview. Setting about the physics, first let's look at what neural networks are. Neural networks are universal approximators, which consist of a layer of neurons. These layers are characterized by activation functions. The weights can be loosely defined as the strength of links between the neurons or the nodes. It is the weights which are adjusted or learned in the training phase to reach the desired result. Also, there is bias associated with each layer. Pins is an extension of neural networks which incorporates the physics of the system through PDEs. These partial differential equations are important in the sense that many engineering problems are defined by the PDEs. So let's look at what a neural network is. Like neural network starts with an input, let's say X, then we will end with an output Y. And in between, the hidden layers forms a complex function, say hx of x and theta. The theta includes both weights and biases. Let's consider a simple network like this is the input. Sorry, this is the input x. Now we have the next layer. We have one single node with a sigmoid function, and then we have the output where we have which is a linear function. And as we said, this will be associated with weights, and we have bias terms, say B1, B2. So what is Y in this network? It will be Y is equal to W2 sigmoid of W1x plus B1 plus B2. This will be the output of this layer, and upon the linear function, Y is defined as this. Now, let's say we have different kind data like x1, x2, and corresponding y1, y2. So for each x1, our network will predict some y1 hat, y2 hat, and for x2 it will be y2 hat. Now to update the weights, which will which is the required metric to reach our result, we use error like y1 minus y1 hat, y2 minus y2 hat. We can use the loss function that we can define as the average of summation of xi minus yi squared. This is mean square error. Now the weights are updated like say weight I is equal to weight I minus alpha into dou L by dou Wi. So each weights are updated by this method. I will take all the values like we have too many of weights in here. All these layers will have weights. So what in a neural network, what we need is we need a loss to calculate the weights. In this case, we need data which is a pair of input as well as output. So for a given input, outputs are complex functions approximated using the hidden layers. And losses are calculated by comparing the outputs with the given data and weights are updated. This is actually a supervised learning process. Now, so the neural networks are trained with backpropagation. It's the most common training algorithm that we use, and we use stochastic gradient descent. And we need a loss function and a lot of data. Now, why we need pins? Like this is a classical example problem in mechanical engineering and all. Like this is a developing flow through a channel, which is governed by these two equations. This problem is a steady incompressible flow through a laminar channel. So in our conventional neural networks, say this will be the conventional neural network to solve this problem if we have enough data points given, like we have too many x, y's and corresponding u velocity, v velocity and pressure. If we have this, we can solve this problem. But in order to get the x, y and corresponding u, v and p, we need the results from any numerical solvers like FEM or FDM, uh, a- from softwares and all. So pins are introduced to solve this problem using neural networks without the data from the numerical solvers. Say, this was the network we saw earlier, which is a conventional neural network. Now coming to physics informed neural networks, let's see what the changes are there. Well, let's see. In our conventional neural network, we had input, hidden layers, and output. In case of physics informed neural networks, these outputs are differentiated and the losses are calculated. We know the loss are important to learn the weights. So let's say these equations were not used in the previous or the normal neural network. But in case of physics informed neural networks, these equations are made use to calculate the partial differential equation losses and the boundary condition loss. Like every problem will be defined by the boundary condition. And if it is a time dependent thing, we will have initial condition as well. Like in this case, the boundary conditions are in top boundary, we have u equal to 0, v equal to 0. Similarly for bottom boundary as well. And in case of the output, we have p equal to 0. And we give an uniform flow in the input. Say we can give uh, u equal to 1, v equal to 0 here. So these four boundaries will constitute the boundary condition loss in this case. Let's say how this is done. Like first, let us take a point in here, which will be x some value, y1 some value. But we know u equal to 0, v equal to 0. So for this point, once the x and y are given, we will get u, v, p for this one value, this one point. But and we know at this point u is equal to 0, v is equal to 0. So like the normal neural networks, we can calculate the loss by ui minus ui hat, vi minus vi hat. That's like the normal case, like we are using data and kind of supervised learning. But the unsupervised learning comes in the interior points, also called as collocation points. So in these points, we don't have any data. Like we don't know what is u, what is v, what is p. So in this case, what we do is we make use of the equations, the PDEs. Like in packages like TensorFlow, there are auto differentiation, which will help us to calculate the differentials so that we can form the PDEs. Let's say we take a point in here and we give the same x and y, we get UVP. But at this point, what we need is the continuity equation to be satisfied. That is dou u by dou x plus dou v by dou y equal to 0. So in order to do that, first we can go to dou by dou x, you can go to dou by dou x, then go here and be here. And similarly, we will go here and similarly it will go here. So inside this partial differential, like in the code, we can define this thing. Similarly, the momentum equations can also be formed using these networks, and we can form the partial differential equation laws. So now we have both boundary equation laws boundary condition loss, and partial differential equation losses. Both these losses are combined here, which will be used as a metric to update the weights. So the difference between the normal networks and physics informed neural networks is in the formation of the loss. Here the outputs are differentiated and PDEs are formed to include the physics of the system as PD loss. And we know the non-boundary conditions are used to calculate the boundary loss. Like it is a supervised process. And like I said, in case of unsteady problems, initial condition loss is also included. Like in the partial differential, in the boundary, like boundary loss, there will be initial condition loss as well. Like here, there will be dou by dou t, and here will be t as input. So this is the difference between, say, physics informed neural networks and the conventional neural networks, where we need corresponding our outputs for the inputs. All the inputs should be associated with an output, but in this case, only the boundary points will have the corresponding outputs present. So this is one of the results that we got using pins, and also we have compared it with CFD solution. Now the remarks. Like pins is considered as a mesh-free approach in solving the PDEs. Like in usual FDM and all, we will have the mesh, and we need to know the delta x, delta y, like to find the differentials. Let's say dou u by dou x will be formed if it is a central difference scheme. So we need a mesh with like constant delta x or dynamic delta x. But usually it is constant if you use uniform meshes. But in case of pins, the points can be anywhere in the domain. We need not create a mesh. Also, the results, while we infer, it can be any other point. It need not be the points which were given while training. So so pins are considered to be a mesh-free approach in solving PDEs. And it is mostly unsupervised learning because, as we see, only the boundary points are calculated, used to calculate in supervised manner. The need of data is limited to problems using boundary and initial conditions. And the pins can be extended to solve the entire domain. Like if we have limited data here, and we need to solve for the entire domain, we can use the pins using data simulation techniques to solve for the entire domain. But still, we are having too many limitations in using pins. Like the computational cost is higher compared to the numerical solvers. And when the complexity of the problem increases, it is kind of difficult to solve using pins. Like we will have too many PDEs to consider. We have to give corresponding weights where all those things will come in. So it will be difficult whenever the complexity increases or high frequency solutions are there. So studies are going on in that direction as well. So that's a brief intro about the pins. And here are some references.